We are live, and thank you so much to everyone who is joining us today. My name is Matthew, and I am one of the assistants in the online class, one of the course staff. We've also got Alexander helping on technical matters, and Professor Impey will start taking questions.
Yes, welcome everyone. Good to be with you again, and we'll start right away with your questions.
The very first question is from Samir, who is on with us live. And the question is, how do we detect Earth magnetism, and where is it moving? I assume they mean the pole. Where is the North Pole moving, or the poles of the magnetic field moving?
Well, I mean, you can detect Earth magnetism with a compass, of course. So just the simplest, smallest toy compass that a child might have that would cost a few cents is detecting the Earth's magnetism. So any magnetized device will detect the Earth's magnetism. The first devices to do that were lodestones. That's a naturally occurring magnetic mineral with aligned grains, and so people would suspend lodestones in liquid or hang it from strings or whatever, and those were sort of naturally occurring compasses responding to the Earth's magnetic field. So people started mapping the magnetic field out hundreds of years ago using this method, maybe even thousands of years ago, in fact. The lodestones were known to the Greeks and the Romans. And currently, of course, we have much more sensitive devices. So the Earth's magnetic field is mapped out well. It obviously is a fluid thing, in part because the Earth has a fluid part of its interior, and so the magnetic field is not tethered in firm rock or solid or metal, but it also has some ability to move over time, especially. So people have plotted the migration of the Earth's magnetic pole over the last few centuries. You can go online and you can see a nice little map of this sort of arcing path the Earth's magnetic pole has traced in its motion away from and sort of circuitous around the geographic North Pole. So it's pretty well known, it's pretty well measured. The mechanism by which it moves in the particular way that it does, that's much less clear because our ability to map out the interior of the Earth is really quite limited. We use sensing based on seismic waves and how they travel through the interior of the Earth, across the Earth, and detect it on the other side of the Earth. So we have very limited diagnostics as to the physical conditions in the interior that are dictating how the magnetic pole moves, but it's also very well measured that it does move. I think the movement at the moment is relatively slow. It's something like a mile per year or something like that, maybe less. So it's pretty modest.
Excellent, thank you. The next question is from Juan Espinoza. Professor, how are there just ring galaxies with no spiraling arms, spiral galaxies with no ring, and others with ring and spiral arms?
So that's an interesting question about the morphology of spiral galaxies. So a classic spiral galaxy, like the Milky Way, like M31, Andromeda, have spiral arms that are wound in different degrees of tightness, depending on whether it's an early or a late type spiral. We are on mid-type spiral, SBC category. So spiral galaxies with rings are actually quite unusual, and they usually reflect an interaction where the interaction between two galaxies leads to a kinetic effect which shocks gas and leads to a ring of star formation at a certain distance from the center. And sometimes this origin of rings is really obvious because there are polar ring galaxies, which are spiral galaxies where the ring is not concentric or in the same plane as the spiral arms, but is almost orthogonal to it in a sort of polar loop. And so that makes it pretty obvious that these galaxies got that way due to interaction. So both of the things that were being asked about in the question relate to different types of interactions or slow speed collisions, slow motion collisions between galaxies leading to this morphology.
The next question is from Hilda, who is on with us live. What changes would affect the Earth when the sun uses all of its thermonuclear energy?
Right, so this is a prospect, an inevitable prospect, because we know the sun is about halfway through its active life as a main sequence star, and that process of being a main sequence star means you're fusing hydrogen to helium. And at some point the helium will be exhausted. Now the sun has a convective region, which means it's sort of mixing its material. It's not sort of fusing from the inside out. Because of that mixing, the sun will consume quite efficiently most of its hydrogen, but of course some hydrogen is left over at the end. So doing the math of how long it takes to exhaust the hydrogen is not trivial, because it depends on how the star circulates during its lifetime. But the models are good enough to say that essentially in about 4 to 4.5 billion years, basically about as long as the sun has been alive, it will have exhausted its fusion source of hydrogen. And at that point, there will be no pressure support. And so without support of pressure from fusion reactions, the core will collapse. And at that point, the sun bifurcates into two pieces of a star. The core collapses and attains a much higher temperature. It stabilizes at a temperature where a certain amount of carbon fusion will occur, from helium up to carbon. And the outer part of the star, as the core recollapses and heats up, that radiation pressure from the hot core drives the outer part of the star, the stellar envelope, out into space. And so that becomes the red giant phase. And that outer envelope, in our case, will reach essentially to the orbit of Mars. And so that's sort of all she wrote for the biosphere at that point, because even though that gas is quite diffuse, it has a very high temperature, of course, and if it moves through the inner solar system and passes the orbit of the Earth, it will essentially toast the biosphere. So we do think that would be the end of life on Earth as we know it, when the star gets to that stage in its life. Now the star hasn't died yet. Some time later, there'll be a planetary nebula phase. The core will collapse with no more energy support and no more fusion to a white dwarf, and that outer envelope will just continue to pass into space and cool down, and that's the fate of the sun.
The next question is from Robert Brady, who's on with us live. Shouldn't gravity feel less as you head towards the center of the Earth because it balances out from other directions?
Yes, that's true. It does, and it would. We can't do the experiment, but it would. So in principle, if you had a borehole that went all the way from the surface to the center of the Earth, and you could somehow descend it, I mean, the temperature, of course, is impossible, so I don't know how you'd protect yourself. If you were at the core of the Earth, and indeed the mass is symmetrically distributed all around you, so you would just essentially be weightless at the center of the Earth. And indeed, as you move down through the Earth, only the layers outside you radially, inside you radially contribute to your weight. And so your weight would just gradually decline by the enclosed mass at your radius. That's essentially what you would see. First person to realize this in the calculation by doing the math, basically calculus, was Isaac Newton. This was a great shorthand for him in working out the gravity of spherical objects in various ways. Another interesting phenomenon, since we're hypothesizing a borehole to the center of the Earth, if you actually made a borehole all the way through the center of the Earth and all the way to the other side, on the opposite side of the Earth to us, and you can imagine passing through that like a tunnel down into the Earth and all the way to the other side. As you stepped into the abyss, you would accelerate by the gravity, of course, through to the center of the Earth. You would overshoot, and you would essentially come to a perfect stop exactly at the Earth's surface on the other side, and then do the same thing over and over again, backwards and forwards. And naturally enough, you're simulating in a passage through the Earth what would be an orbit of the Earth, and so the time taken for one complete passage through the Earth to the other side and then back to where you started with zero velocity is 90 minutes.
Excellent. Thank you very much. Just for listeners, I see all of your questions about phosphine on Venus. We're going to get to that next. I just want to make sure that we've had time for stragglers to get in before we talk about it, because I know lots of people are interested in it. So we'll do another question, and then we'll do the Venus phosphine question. So Daniel would like to know, where is the universe expanding into?
Everywhere. The universe is doing an isotropic expansion in 3 dimensions, which means it's expanding uniformly in all dimensions. And that means that every point in space, time in space, is moving away from every other point in space. So if we were situated on a distant galaxy, observing other galaxies, they would move away from us and partake in a Hubble law expansion as the galaxies we see from the Earth do. So it's not expanding into anything, and it's not expanding differently in any direction. It's a uniform three-dimensional expansion as seen at any point in space.
All right, the next question is going to be about phosphine. So we'll take a couple questions about phosphine on Venus. So first of all, could you just explain the discovery, what was found, and what you think the chances are of it being life, like all the headlines say?
Right. The cautious headlines don't claim with any lack of doubt that it's biology, because you simply can't say that. Phosphine is a small molecule that on the Earth is found in association with biology. It's important to make that distinction because it's often seen in the interior of the Earth, in places where microbes exist in rock space and under extreme conditions. And no biologist has proposed the exact mechanism by which phosphine is used in biological organisms. It's not part of an obvious metabolism, but it's implicated in the metabolism of microbes. So that's an important distinction. It does indeed seem, however, that phosphine is associated on the Earth with biology. The only other way phosphine can be produced without biology is under pretty extreme conditions of heat and pressure. So when you go to Venus, that distinction is also important because Venus does have extreme conditions of heat and pressure on the surface or near the surface. And so what matters here is that phosphine was detected spectroscopically by large ground-based telescopes with great sensitivity of the spectroscopy. It's a small, very trace element, I think, few parts, tens of parts in billion, I think. And it was detected in the mid-cloud level, the mid-cloud decks, if you like, of Venus, which has an enormously thick and dense and toxic atmosphere. So it's important that it was detected in the mid-level atmosphere because that's a region that's tempered enough that we don't think it could have been produced by natural processes, chemical or geological processes. So we're falling back, and the astronomers have fallen back on the fact that it's implicated on Earth with biology, and so they make the same inference on Venus, which is interesting, of course, because Venus was thought to be a dead world, and now we're talking about life-tracing ingredient found in the Venusian atmosphere. Now this calls to mind a famous paper that was written by Carl Sagan and Ed Salpeter at Cornell. They were both at Cornell when Carl Sagan was early in his career, and I can't remember the year, I think it was 1972, but they wrote a paper speculating about life forms, buoyant sort of jellyfish-like life forms that could exist in the mid-level clouds of Jupiter. Could there be living creatures there? And it got published in Nature, a very serious scientific journal, peer-reviewed. Some people thought they were being flip and just obviously speculating in a not serious way, but they insisted they were serious. They were just making the point that it's very hard to rule out unusual forms of life in these unusual environments. So having had that speculation decades ago, now we have another incident where it appears that there might be life in the atmospheric zone of a planet that's normally very hot at its surface and that we hadn't thought of as a living planet or even a habitable planet. Well, that's pretty interesting. And so that's the nature of the discovery.
All right, so that was, lots of people have asked that. So Ajith, Tony, and Ezekiel sent an email saying, how is this different or potentially different from previous discoveries of supposedly biological biological systems on places like Mars?
Well, the real difference is that it's potentially a living organism that exists in a gaseous environment, in an atmosphere. Now, is that even possible? Because all life on Earth has either been found in the deep sea or on the surface, of course, and occasionally in rock, in deep rock. But there have been detections of microbes that have been found in the stratosphere. It's not clear they have their in full life cycle in the stratosphere, or they're born and generated on the Earth's surface and then are carried by currents or convection into the upper atmosphere. But viable organisms have been found in the high atmosphere of the Earth. So it is possible for living organisms, microbes, to exist in a gaseous environment. We know that from the Earth. And so for it to happen on Venus would be pretty unusual, because Mars life, we're not expecting that way. Mars life, we're going to look for either underground in aquifers, assuming there's still water there, liquid right now, or in fossilized form in places that used to be lake beds, shallow lake beds or seas. That's how people are looking for life on Mars. Mars has a very thin atmosphere. Nobody really expects you could find microbes in that thin atmosphere, which is dosed with UV radiation and cosmic rays.
The next question is from Amar, who sent an email asking, how is it that planetary rings form and persist? And then would also like to know if planetary rings somehow affect orbital eccentricity, or a planet's orbit, I suppose.
So planetary rings, the persistence of planetary rings is actually an intriguing issue, maybe even a problem in planetary science, because people have argued with not too much evidence to sort out the problem of how long planetary rings can and should persist. We do think that the planetary rings form as a byproduct of formation of a planet. So when a planet forms, it's a miniaturized version of the formation of the solar system, and some of the material left over that's insufficient and to accrete into a moon may form a ring system. And that's the general picture of how Saturn's rings formed, and we know the other three giant planets have ring systems too that are much less prominent. But when you actually do calculations and simulations, you have a hard job persisting a ring system, even Saturn's ring system, for 4.5 billion years, which has led to a problem, because if it didn't form when the planet formed and the solar system formed, and it can't last 4.5 billion years, then what happened? It must have formed later, or it must have replenished somehow. And if it replenished, then from what source? And these are not quite resolved issues in planetary science, actually. I'd say we maybe don't know the formation process as well as we do. So they are long-term persistent features of a planet, clearly. They can last billions of years. But they don't last forever, because there is attrition or ablation or evaporation, if you like, eventually of the ring system. The particles collide. Their collisions will send some particles free into a liberating velocity away from the orbital, away from the gravity of the planet, and it'll send other particles inward that will fall into the planet atmosphere. So the ring systems are not very, very long-term stable, by which I mean many billions of years. They will not last forever. And so I'd say, you know, as interesting and familiar as the ring systems of the giant planets are, there are still some things we actually don't understand very well about them.
Swarendu, who is on with us live, would like to know, why is the Earth's core still so hot? Why hasn't all the primordial heat radiated out into space during the past 4 billion years? And are all planets super hot on the inside?
The basic reason that the Earth's core is still hot is it's because it's continuing to generate heat by radioactive decay of heavy elements that just occur naturally within the rock. That's the fundamental reason. When people were worrying about what the age of the Earth was or how they would measure it, they did experiments. A man called Comte de Buffon, French aristocrat who was an amateur scientist, I think in the late 18th century, like 1770s and so on, he was wondering how to measure the age of the Earth, and he basically took metal spheres and he got them to a very high temperature in an oven, and he watched how long it took them to cool to room temperature or to radiate all their heat. And as he got bigger and bigger spheres, the time for them to cool was longer and longer, and then he extrapolated up to the mass of the Earth and the size of the Earth, and he deduced that if the Earth had metal in its core that had originally been hot, near molten, it should have radiated all its heat away within hundreds of thousands or maybe tens of millions of years. And so it shouldn't be billions of years old. So even a few hundred years ago, we knew there was something else going on than simple cooling of an initially molten material. And that extra ingredient, not known in 1770, of course, was radioactivity. So once you put in the extra heat from radioactivity, then you can explain why the core of the Earth is still as hot as it is.
The next question is from Ben, who also has a planetary science question. I'll make it more general and then add his piece. So the general question is, how is Vallis Marineris formed? And then his specific one was, what are the odds that it was caused by an electrical discharge?
Yes, so Vallis Marineris is a huge geological feature on Mars, where the largest geological scar almost in the solar system. It's interesting that Mars is a relatively small planet, substantially smaller than the Earth, and yet it has Vallis Marineris, which is the largest sort of geological feature of any kind that we know of in the solar system, and has the largest volcano, Olympus Mons, in the solar system. That's kind of interesting. So some of the reasons that Mars has such huge geological features is that Mars was, but is not now, geologically active. So we know from the age map of the surface of Mars that most of Mars' surface is quite old. It's just lost its atmosphere and been cratered over many years, and no lava has flowed for a long time. But there are younger areas of Mars, and it seems like the volcanism and geology of Mars is not symmetrically distributed around the planet. So some parts of the planet have had extraordinary amounts of volcanism in the distant past, and that's what's led to these extraordinary geological sized features like Vallis Marineris. That era of Mars history is long gone. Mars, if not geologically dead, is close to geologically dead now.
The next question, while a little bit specific, I think we can generally talk about it. So Natalie is a former astroparticle physicist who would like to make some contributions, but would like to know generally, what areas in astronomy do you see as most underserved and under-researched?
That's a good question. I mean, astronomy is there are trends in astronomy that make some areas hot. Exoplanet research, of course, is very hot right now because there are so many discoveries. Almost every week something interesting being said. So astrobiology and exoplanets are hot and definitely not underserved. And objects that are always catching people's attention, like black holes and neutron stars, I wouldn't say they're underserved too, although the professional communities that research them are not that large. One of the underserved areas is actually work on supernovae, because the observational data on supernovae is fairly sparse, because since supernova 1987A, we just haven't had a nearby supernova to study in detail. So supernova research still depends quite heavily on models and simulations, and it's very difficult to do the theory of supernovae because of the extreme conditions. And that community is also very small. So supernova research seems to be a little underserved at the moment. And just in general, stellar astronomy is less popular or trendy, if you like, or less well funded perhaps as well. I've seen the NSF statistics than cosmology and galaxies and so on. So that's probably the area I might point to.
The next question, several people have asked this, but Bob Ravi in particular says, if light is absorbed by black holes, how is it that we detect their location and have pictures of one?
Right, so if nothing can come out, then how do we know they're there? Because we obviously can't bounce light off them. So it's indirect. The only black holes that represent dead stars or stellar corpses, the only black holes we know of that we have good evidence for are in binary systems. So that's the basic answer. We don't detect the black hole itself. We detect it in a binary system where the companion is a very luminous star, usually a giant star or supergiant. And it's the orbit and the application of Kepler's law that tells us the companion is a dead star with a mass more than 3.5 times the mass of the sun, which fits the definition of a black hole. So in all the 50 or 60 really good quality cases where data points to a stellar mass black hole, it's in a binary system. Now, black holes at the center of galaxies, the type of evidence is a little different. And the one galaxy we have a picture of a black hole made at long wavelengths, not a visible picture, is M87, a giant elliptical galaxy about 65 million light years away. And so galaxies have black holes at their centers, and they also attract mass. They attract mass that falls in and disappears, of course. But in the vicinity of the black hole, which is almost always rotating because it forms in a rotating system, you have an accretion disk. And so it's the accretion disk that you tend to see. And so that picture of M87 that was front page headlines a while ago, last year or 18 months ago, the silhouette of the event horizon as being black was clear, but the bright region, this asymmetric bright region, was the accretion disk, the very hot gas plasma spiraling and orbiting right near the event horizon itself. So it's always this kind of indirect probing of the black hole that gives us the information about it, not seeing the black hole itself, which is indeed black.
The next question is, can you shed any light on the growing problem of space junk? Talk a little bit about what it is and why is it a problem? And they say that it can trap us on Earth for centuries.
Yeah, space junk is a growing problem. It's been a problem for decades. It's just getting worse because as we put more satellites up, those satellites, they are not always automatically taking care of themselves. So satellites in low Earth orbit experience enough drag that once they've extended, gone past their usable range, they will eventually degrade their orbits, and the drag of the very thin upper atmosphere will eventually cause them to spiral into Earth, and they burn up in the lower atmosphere. So some space junk takes care of itself, but space junk in the range of 200 to 300 miles, the sort of range of the Space Shuttle and the International Space Station, and a lot of orbiting big satellites that are not going to deorbit naturally, this is the stuff that will stay there almost forever. And when pieces fall off a satellite, when satellites just get naturally destroyed by a meteor or a piece of rock from outside, then the shrapnel increases and the little pieces hit other pieces and so on. In the space station, pretty much once or twice a year, the astronauts, whoever's in the space station at the time, have to take shelter in the central hub, the safest part of the space station, because of a proximity alert with a very fast-moving piece of space junk. And the typical relative velocities are tens of thousands of miles an hour. So a tiny piece the size of a head of a pin can punch a hole in the skin of the space station, and a piece of space junk the size of a golf ball is catastrophic for the space station. So we know it's a problem. We know it's getting worse. Chinese were extremely antisocial and blew up one of their own satellites as an experiment a couple of years ago and made a lot of space junk in one fell swoop, and that was extremely annoying to almost everyone in the space program. There are technologies people are exploring to try and mitigate it. There's one technology that was in the news just a week or so ago. It's essentially a sort of space net. So it's a satellite that will deploy a net that unfurls, and it can be charged. And because you can charge this space net, its electric field interacting, typically inducing an similar electric field in the metal that most space junk is made of, will let it be a sort of electromagnetic scoop, and this net can actually troll space junk. The math is very unfavorable, though. Even with a net like that, you'd need a net that was tens of kilometers in diameter or size, and you need to run that net for decades or hundreds of years to scoop up any significant fraction of the orbital surface area where their space junk exists. So no one's found a mechanism that is efficient enough, given the vastness of space, even near Earth orbit, that's a vast real estate, to solve this problem. And at the moment, it's an insoluble problem, I would say.
The next question is from Sai Krishna, who would like to know, how is the data that is collected from telescopes converted into images?
Well, that's a good question because it's very basic to how astronomy works in the research domain. Most optical telescopes are taking their pictures or their spectra, whatever data they take, with CCDs, charge-coupled devices. CCDs astronomers use are just very fancy versions of the CCDs in your cell phone or in all the cameras, digital cameras. So there are literally hundreds of millions of CCDs in the commercial electronic sector, and the astronomer CCDs are just bigger versions, more efficient versions, larger wavelength range, less blemishes. They're just very perfect, high-performing versions. So what these CCDs do is they're made of silicon. They have arrays of pixels, and essentially when incoming light converts into electrons in the semiconductor, and the electrons fill these potential wells in the silicon. And so the capacity of the silicon or the CCD to detect light depends on how efficiently it can convert photons into electrons and over what wavelength range. And it also depends on having a very low natural noise level in the silicon, because you don't want electrical noise to confuse you relative to the electrons that are created by photons from coming in from space. And most CCDs have well capacities of hundreds of thousands of electrons, so that's a pretty good dynamic range. They can detect very faint signals and also very bright signals. Those electrons are accumulated for the time you're exposing the CCD to the sky. When you close the shutter, there are readouts where the electrons can be read. It's a pixel array, typically 4,000 pixels on each side, or 8,000 by 8,000. Those are typical numbers. So that's a lot of pixels. That's if it's 8,000, it's obviously 64 million pixels. And so you basically read out the electrons, count the electrons in two dimensions. You read along a row, and then you read down the columns. And when you've read the electrons, you're making an electrical signal, because electrons passing through a wire is an electrical signal. And so when you have that electrical signal, which is digitized, it's sent through a digital converter, you then can convert that electrical digitized signal into a light intensity that you show on a monitor, or into just numbers that you transmit the data to the astronomers. A requirement of the CCD is that you be able to read it out pretty quickly, because having looked at the sky for 20 minutes or an hour, you don't want to take the same amount of time to get that data off. So these electronic devices have to be able to read out their 64 or more million channels very fast, typically within less than a minute. So that's a sort of requirement of the electronics. And this is all very mature. These techniques have been around starting in the late 70s, and in the last 2 or 3 decades, it's completely standard procedure. And of course, you can buy a CCD package for a small telescope if you're an amateur astronomer, and it works pretty much the same way.
Thank you very much. The next question is from Boone, who's on with us live. Do you subscribe to the theory of multiple universes or parallel universes?
I don't subscribe strongly to it, but I recognize that if you like the idea of inflation in cosmology, then you are driven to some idea that's like the multiverse. So inflation is the addition to the standard Big Bang model made in the 1980s, early 1980s. Alan Guth most famously proposed it, but there were several other theorists involved, which tries to explain the smoothness and flatness of space-time by hypothesizing a very rapid exponential phase of expansion in the first tiny fraction of a second after the Big Bang that smooths the universe out and flattens space-time, and so delivers a universe that looks like it does now. If you don't have that mechanism, you're forced to put the smoothness and flatness of the universe we live in down to initial conditions early in the universe, which look like they're very finely tuned, and there's no reason for them to be that finely tuned. So it's a little awkward each way. If you don't have inflation, you have a fine-tuning problem. If you do have inflation, you're left with what's the physical mechanism that caused the universe to exponentially expand so early on, very close to the Big Bang itself. The mechanism or the theory of inflation is really not very well worked out, and that's a sort of different question. But the exponential expansion of the universe early on also implies that it emerged from a quantum state. And so it's the combination of the fact that the visible universe we live in is a small fraction of the overall space-time. Once inflation has occurred, there's large regions of space-time we can't see, separate from ours, and the fact that the universe we live in expanded in a sense from a quantum state that leads to the idea of the multiverse being another set of universes, unobservable to us, parallel to us because they're in distinct space-times, and possibly originating from different quantum fluctuations and therefore having different properties, different laws of physics. And that's, in a nutshell, is the multiverse idea. So if you held to standard scientific method, you'd say, well, what are the unique predictions of the multiverse idea, and how can we test it and show whether it's true or not? And multiverse hasn't really satisfied that criterion yet. There are not any real unique predictions of what the multiverse means or how we would test it, nor have there been any tests of the multiverse to date. So I would say it sits in limbo. It's a not completely valid scientific idea, but more of a speculation.
Next question we got from several participants. Parth and Lakshmi are both interested in neutrinos. So can you explain how it is that we detect neutrinos? Is it even possible to detect them?
It is, and neutrino astronomy has been around for a while. The first neutrinos were detected. Obviously, neutrinos have been in particle physics for almost a century. So neutrinos were anticipated. They were predicted in quantum theory by Wolfgang Pauli, I think, in the 1920s. And then they were unobserved for almost 20 years, and they were finally detected. So we've had detection of neutrinos in laboratory physics situations for quite a while. In astrophysics, it's more recent. The first neutrinos were detected from the sun in the starting in the late 1960s and into the 70s by Ray Davis, who had a neutrino detector that he operated out of the University of Illinois. And these detectors are typically underground to shield them from contaminating and confusing events. They typically involve extremely pure liquids. And when the neutrinos interact very weakly with matter, but if you have a big enough and pure enough detector, you can see their very occasional interactions. The Ray Davis detector was essentially using cleaning fluid as its matrix for detecting neutrinos. So typically, you're actually looking for mechanical energy deposited into the material by collision with the neutrino, because even though they may have very low mass, they're traveling essentially at the speed of light, and they can have quite high energy. And a neutrino deficit was detected from the sun, 1/3 of the expected theoretical signal. And so while neutrinos were detected from the sun a long time ago, decades ago, it was the wrong amount, and so it led to a sort of crisis in the theory. Now we believe neutrinos can oscillate between their 3 different flavors by mechanisms not completely understood. It's called the seesaw mechanism. And neutrinos have now been detected from other places too. Another means of detecting neutrinos is to put the neutrino detectors, suspend them in ice, and find very pure regions either of seawater or in a deep sea trench, or of ice in the Antarctic ice pack. And there the water crystals, or the water itself, forms the pure medium for detecting the neutrino. But again, it's by collision, and hydrophones are used to detect the sort of acoustic energy that results from the collision. These are very hard events to detect, but they have been detected, so neutrino astronomy is a real thing. We detected neutrinos from supernova 1987A, other supernovae, and probably from a number of active galaxies. So neutrino astronomy is sort of rapidly maturing.
Excellent, thank you. And then kind of a related or follow-up question is, what information can we get by capturing neutrinos that are emitted from or emitted by the sun?
The best information we get from the solar neutrinos is a strong constraint on on their mass, actually, and the stellar model, because the sun is a very well-modeled star. We measured it in enormous detail. And neutrinos are predicted to be a result of the nuclear reactions that lead to sunlight, the fusion of hydrogen to helium. As a byproduct, neutrinos or antineutrinos are emitted. So it's a core part of stellar astrophysics and solar radiation to expect that neutrinos are detected. And it's obviously the nearest source of neutrinos, so we've detected those neutrinos for half a century, and we continue to detect them. What we hope to learn from the neutrinos from the sun is, now that we know that we're seeing only part of the picture because neutrinos can change their flavor, we've now got different neutrino detectors that can detect the different flavors of neutrinos. Remember, there's electron neutrino, tau neutrino, and muon neutrino. And they can change from one flavor to another naturally by this oscillation mechanism. So it takes different detectors to detect the three different flavors of neutrinos because they have different masses and energy ranges. And so the next stage of the neutrino detection from the sun is to try and pin down this mechanism by which neutrinos change their flavor, and ideally to measure the masses of all those three flavors of neutrino, because when we do that we can decide whether neutrinos have any role in dark matter. They can't be the bulk of dark matter, but they could be a component of dark matter in the universe.
Thank you. Hernan Reyes sent an email and is on with us live. You've explained the Doppler method and the transit method for detecting exoplanets. However, neither of these methods work from Earth if we are looking down on the North Pole, say, of a planet or a star. Will be out of the axis. So what is the method for, or are there any methods for detecting these kinds of exoplanetary systems?
Right. It's true that both of those primary methods through which most 95, 98 probably % of all exoplanets have been found have a strong preference for for planets in the equatorial plane. In fact, the transit method requires them to be very close to equatorial. Now, the Doppler method is not so insensitive in the sense that only when you're looking exactly pole on is the Doppler component that you can measure 0. Even at an angle of 5 or 10 degrees, you still get some component of the Doppler shift. So the Doppler shift is more sensitive to various orientations. But yes, it's not sensitive to the perfect pole on. The method that is most sensitive to the pole on is actually the method of direct imaging, because if you know you're looking pole on to a planetary system or just some modest angle to pole on, you know that the planet around the star is always going to be separated from the star because you're looking at its orbit from above, basically. And so imaging is the method, basically, that's immune to this selection bias and in fact gives you the most reliable results when you are pole on. And so that's a method that unfortunately is not as effective as the other two. So we've only imaged 60 or maybe 70 exoplanets, and it's very hard to image Earth-like planets. These are mostly Uranus and Neptune sized or Jupiter sized. But that's the answer to the question.
Excellent, thank you very much. The next question is from a live participant. Pakornan would like to know if you know anything about the future of the New Horizons space probe.
I'm not sure, actually, of the New Horizons space probe, since it's sort of mostly finished its mission. It's not really possible with the limited rocket fuel available or thruster fuel available on these spacecraft to change their trajectories. And for a spacecraft that's moving at extremely high speed to get to its destination, that's essentially the end of it. It just sails off into space, and if it's headed for the outer solar system, into the region between stars, as the Voyager probes and the Pioneer probes left the solar system years and decades ago, then that's the same fate for the New Horizons probe. I know that its instrumentation is still alive, though, so it will continue to transmit data, and I presume it's going to start looking at the Kuiper belt.
The next question is from Ayush, who's on with us live, who would like to know what kind, if any, of waves are generated during a supernova or star explosion. I'm assuming that they mean gravitational waves, but maybe you can just talk about that process and talk about how gravitational waves relate to supernova or stellar explosions.
So stellar explosions of different kinds, novae, which are recurrent explosions, or supernovae, which are final detonations of an evolved star, and there's no explosion after that, there's just a remnant. They emit normal electromagnetic waves, of course, across the electromagnetic spectrum, including particularly up to high energy, because the instantaneous temperature in a supernova blast wave is actually several billion Kelvin. So you're making electromagnetic waves to very, very high energy gamma rays. But as far as if the question relates to gravitational waves, then that's a very interesting situation, because that's a type of gravitational wave that we haven't succeeded in detecting, but in principle it's possible. The strongest gravitational wave signatures come from the most compact objects and their interactions, and so black hole mergers, neutron star mergers, or black hole neutron star mergers. However, a supernova, if it's not completely symmetric in its collapse and explosion, which is often the case, the asymmetry itself will create gravity waves, the change of the mass configuration, essentially making ripples in space-time. So supernovae are predicted to be a source of gravitational waves, and I just don't think we have sensitivity in the current instrumentation to see them. But probably in the next 5 to 10 years, or as this gravity wave arrays increase, to the point where we don't just have 2 LIGO arrays and the Virgo detector and maybe one in Japan, but there's eventually going to be detectors in India and elsewhere. So we may end up with 5, 6, 7 gravity wave detectors all working together, and at that point you get the sensitivity to probably pick up supernovae.
Excellent, thank you very much. The next question is very simple. Shangi would like to know, is time travel possible?
Not that we know of. The reason we don't think it's possible is a couple of reasons. The first is the linear nature of time. So while time is distorted in general relativity, time slows down in an intense gravitational field. That effect has been measured. There's nothing in general relativity that suggests you can reverse time. So although you can manipulate time with gravity and slow it down and change its pace, you can't reverse it. And time travel essentially is always looking at something that will reverse time. The more profound reason, so it's not part of a physical theory of gravity, for instance, or special relativity, which is also does not allow that possibility. Speed of light is an absolute limit, and it's invariant. The more profound scientific reason we don't think time travel is possible is because it would create a violation of causality. It's a foundational principle of science as we understand it, any kind of science, not just astronomy, that effects have causes that we can identify. There's a cause, and then there's an effect, and we observe the relationship between the two. To have effects preceding causes, which would be implied if we could reverse time's arrow or do time travel, would really violate a profound premise about how science works, and really about how the natural world works. So basically, if time travel were possible, or if it were possible to jump backwards and forwards in time at will, you could set up situations that were essentially hugely logically problematic. And that's a logical reason, if you like, a philosophical reason almost, why we don't think time travel is possible.
Excellent, thank you very much. I want to acknowledge that there are a couple questions in the live chat about things like telescopes and amateur astronomy, and we probably won't get to those today, but we do have a way to deal with them in the future, and if you stick around till the end of the session, we will talk about upcoming opportunities for that. The next question is from John McCluskey, who sent an email, and John completed our course 6 years ago and is back to follow up and ask some live questions, so thank you for joining us. The tidal bulge in Earth's oceans that faces towards the moon seems fairly straightforward to him. However, why is there a bulge on the opposite side of the Earth facing away from the moon?
Right. Well, first of all, welcome back. 6 years, that's a long time. That's not long after we started our first MOOC in 2013. So you're a very early adopter and taker of the course and an alum, so great to have you back. Right, the tidal force is a stretching force, and so it applies equally to both sides of the Earth. The way to sort of think of this is take a spring or a slinky, and if you marked out 4 points on the slinky, 1, 2, 3, 4, and 1 and 2 were the top and the bottom of the ocean on one side of the Earth, and 3 and 4 were the top and bottom of the ocean on the other side of the Earth, and then you stretch the slinky, as would happen in a tidal stretching force, then the gap between 1 and 2, that is the top and bottom of the ocean on one side of the Earth, and the gap between 3 and 4, the other side of the Earth, increase both almost at the same rate. So it's because it's a stretching force, that stretching applies regardless of what side of the planet you're on, because for example, if you're talking about the sun, which is very far away, the difference in the distance from the sun between the far side of the Earth and the near side of the Earth is a tiny fraction difference. And so the stretching force is not very different at all on the far side of the Earth and the near side of the Earth. And so the tides happen on both sides of the Earth, and as the Earth rotates, you have 2 tides a day.
The next question is from Varun, who would like to know, there are red stars, orange stars, yellow stars, and blue stars, but why no green stars?
That's a good question. So you have the rainbow, red, orange, yellow, green, blue, indigo, violet, the classic colors of the rainbow. And you might naturally imagine that stars might have all the colors of the rainbow. Of course, when you go outside and look at the night sky, even though you're looking at stars with a big range of surface temperatures, they don't really show those dramatic colors. And the basic reason for that is that stars with a particular temperature they're nothing like monochromatic. The stars have a very large range of radiation. It's a blackbody spectrum. So it spreads over a factor of 5, 10, 15 in wavelength, whereas the difference between the reddest red and the bluest blue is only a factor of 2 in wavelength. So there's not a lot of specificity about the temperature and colors of stars which radiate as black bodies. That's part of the reason. So most of the stars, the most you might see is a star that looks just a little pinkish or a little orangish compared to one that looks a little whitish or a little yellowish. You're just not going to see the green part of the spectrum, which is a really narrow slice of a narrow wavelength range. That's the fundamental reason why you won't see a star that way. Not only is the radiation spreading out over many wavelengths, the eye is also not a monochronometer. In other words, the eye is not a device that recognizes one wavelength and picks out the green and picks out the red and picks out the blue. The eye recognizes a full range of colors and combines them all in software in our brains. But it doesn't specifically detect green above other wavelengths and therefore represent something as looking like a green star.
All right, the next question is from one of our young viewers who would like to know, how is it that we get order, like if the universe forms structures and seems ordered, from a chaotic beginning? So how does order form from chaos?
It's a good question. It's mostly gravity. So the chaos of the early universe amounts to saying a lack of structure. So when the universe is young and chaotic and there's a lot of radiation and there's not much variation in the properties from one place to another, it's chaotic and random pretty much. And it's also pretty smooth. There's not much difference between one place and another place in temperature or density. As the universe gets older and cooler, and especially after atoms form and then the radiation dilutes, the radiation for the early part of the history of the universe is essentially stopping any structure from forming or preventing it from being unchaotic. But once the radiation reduces in energy and gravity can cause structures to form, now you have the chance to deviate from the chaos and start to generate structures. Gravity is an inverse square law, so it has infinite range, and that means it has a very long reach. And so as the universe is expanding, gravity is pulling in or exerting a sculpting force on matter over very large scales, all simultaneously, small scales, medium scales, and large scales. So it's weaker gravity on long scales, but there's more stuff on long scales, so it can make big things form almost as well as it can make small things form. And so over a period of time, we think it took maybe 100 or 200 million years after the Big Bang before the first galaxies and clusters formed. But then it's just a very steady process. So you are gradually emerging from chaos and randomness into a world of structure, if not complete order, because of gravity operating.
All right, the next question is from Lakshmi, who is asking generally, why is Elon Musk so hyped up with terraforming Mars? Wouldn't it be more efficient, or wouldn't it be better to use the money for mining asteroids or something like that?
Yes, I tend to agree with you. Elon Musk says a lot of things, and with Elon Musk, who's a very clever man, you have to deconvolve the things he's saying that are motivated by a commercial interest, like getting money for SpaceX and keeping that research and development going. Things that are motivated by scientific curiosity, because he is a scientist, and so he's curious like any scientist is. And then things where he's just trying to create publicity and create interest, because he's got an eye on social media. He likes to keep his profile pretty high. He doesn't like to be out of the public eye. So I would say that his comments about terraforming are in that third category. That's where he's really just trying to get attention. I don't think he realistically believes terraforming is anything his company can do or any company can do in the short term. But he recognizes it as a very evocative idea. The idea that we are trashing our own planet, unfortunately, as we speak, making it less habitable. The fact that Mars was once habitable, we think, and could potentially, through technology that's not, beyond the bounds of possibility, render it habitable once more. So you put those pieces together, and it's a very powerful idea. And he knows it's a powerful idea, which is why he likes to talk about it. But he's also an engineer as well as a scientist. He's an engineering physics PhD, I think, was his flavor of PhD. So he knows that terraforming Mars is a fantastic project that would cost many trillions of dollars and take many hundreds of years to execute. There are no showstoppers. I mean, other technologies to do it all exist, or you could make them work. I think he's just trying to draw attention to Mars in that way. He, more realistically, is aiming for a Mars base before he dies, because he said he wanted to die on Mars. So that's his real midterm goal, not terraforming.
The next question is from Aishwarya Lakshmi, who sent an email. And the first two questions are related. So why does the Earth or any planet spin? And why do planets sometimes get tidally locked?
So the spinning of a planet is really due to initial conditions. It's due to what material they formed from. So the solar system, of which our spinning planet is a part, formed from a very large diffuse cloud of gas, that the size of which was dozens or hundreds of times the solar system size now. And in the sort of chaotic nature of interstellar and intergalactic material, almost every region of gas will have some small amount of net rotation. So there are sort of physics principles which say that you'll have small amounts of rotation. And when that rotation, when an object collapses, that rotation is amplified by conservation of angular momentum. So when the solar system formed, it formed a disk, conserving angular momentum, and the disk was rotating more rapidly than the initial, much bigger gas cloud. And the planets were they were part of the same angular momentum of that whole system. So at the place where a planet would form in the rotating disk, the solar nebula, it has a certain amount of angular momentum, and any subset of that gas or material would share that angular momentum. And so we have planets that all spin in the same direction that they orbit the sun. And that makes sense. That's just saying they all share the same initial angular momentum. So that's why the Earth spins the way it does. What was the second part of the question? I forgot the second.
And then it's, why do some planets get tidally locked?
So tidal locking is a different question, and I'll answer it as a separate thing. Why do planets get tidally locked? It only happens when a planet, it can happen to a moon of a planet, or it can happen to a planet around a star. So in any orbital scenario where you have a smaller thing orbiting a bigger thing, if that smaller object is fairly close to the large object compared to its size, then you have the possibility of tidal locking. So we already talked about the tidal force, which is the stretching force that applies when the gravity on the near side of an object is significantly different than gravity on the far side of the object, and that acts as a stretching force. Well, it's that same tidal force that's responsible for tidal locking, because when a moon or a planet is close to its larger gravitating object, then that tidal stretching and therefore also tidal locking force is stronger, and so it's more likely that an object is going to get locked in with one face always pointing to the star, or if it's a moon, one face of the moon always pointing to the planet, like the Earth's moon. So in the Earth's moon case, it's because the moon is one of the largest satellites in the solar system, and it's relatively close to the Earth. In the case of Mercury, it's because Mercury is very close to the sun compared to any other planet.
And then the last part of the question is, why is it that planets sometimes have tilted axes?
So the tilt of the axes of planets is, we think, the initial conditions in the simple version of the geometry would be you wouldn't expect any axial tilt, because if the angular momentum of the disk that formed the planets, it has a certain orientation, you'd expect the pieces of that system that collapse by gravity to share that angular momentum, so their vectors should be aligned. So in an idealized situation, there should be no tilt of a planet's axis. They should all just be vertically aligned. Now in practice that's not true, and it's because planets interact with each other. So even though the planets in our solar system are fairly far from each other, they do interact gravitationally. And those interactions, especially the ones that occurred early in the history of the solar system when planets were actually migrating, they were actually moving their wholesale positions relative to the sun, those interactions definitely can cause a tilt of the axis. Remember that the planets are not all orbiting in exactly the same plane. There's a variation in their angle relative to the ecliptic, the Earth-Sun plane, by 5 degrees or so. So you'd expect something like 3 to 5 degrees of axial tilt just naturally because of the thickness of the system. When you add in interactions between the planets or interactions with passing objects near the solar system that then moved on and we don't even see them anymore, then you can have things moving quite a lot away from just a few degrees to the 15 to 25 degrees that includes the Earth and Mars.
All right, the hour for our live session is up. We will take one more quick question, but before we do that, I just wanted to mention to everybody that we are our team collectively is going to be starting some new streaming opportunities on a different service. We don't want to be penalized by YouTube for mentioning that, so unless we clear that up, I don't want to specifically point you there, but I do want to let everybody know to look in your emails from the course and check out the Discord server, and we'll be announcing some upcoming streaming sessions, some live streaming sessions from other members of our team, and eventually Professor Impey will be doing some live stuff over there with us as well. And on Wednesdays, we'll be talking about astronomy news, and Fridays, we'll be talking about amateur astronomy. More information will be coming out soon. And then to wrap up, Frank would like to know, when are you going to conduct another online course? He's particularly interested in dark matter, dark energy, and the birth and death of galaxies. But I thought you could talk about our next course that we're working on.
Sure. It will be nice to have a cosmology, just a pure cosmology class. That's one that I would certainly consider, to get deeper into these subjects, because they do exert a lot of interest, a lot of curiosity for people. But the one we're actually getting much closer to launching, in the sense that we've already filmed the videos, is we're going to do a history and philosophy of astronomy course, and that will go up on Coursera, hopefully by the end of the year. Yeah, I think for sure by the end of the year. And the goal there is to really cover the full sweep of the subject, the full, from prehistory through the Greek scientists up to the modern day. And by taking not just the history part, but the philosophy part, it allows us to go into some deeper issues like quantum theory and some of the conundrums of physics, as well as astrophysics that relate to philosophy or our place in the universe. So we will give heads up for that, of course. Meanwhile, thanks for your questions. They were good ones as always today, and we'll be back with you next week.